Good afternoon, class. In today's video, what I wanted to do was to talk about length contraction. Of course, this is relativistic length contraction, and first of all, what does that even mean? Conceptually, it would be something like this. If you have a normal inertial reference frame like this one, which I'm going to call S, and then I've got a moving reference frame S primed, then what will happen is in the direction that that frame of reference is moving, the length will start to contract based on how fast you're moving. Now, of course, what does that look like? By how much? Those are all good questions, and so we will continue this, and that's why I did the Lorentz transformation series before this, because then it makes this whole video actually much easier to understand. So here we go. So if let's say we've got a rod, and it's got a length of L, which is x2 minus x1, and then we've got the same rod, but it's now moving in a non-inertial reference frame, x prime 2 and x minus x prime 1. We get that because we're just measuring points on the coordinate system to determine the length of this rod. So in the inertial reference frame, it's very simple. What is the length? It's just x2 minus x1. Easy. However, in the non-inertial reference frame, especially because when we get up to relativistic speeds, the length of it is going to be L prime, which is x prime 2 minus x prime 1, and that's of course due to the Lorentz transformation. So of course, if we're going to do that, we need to actually put in those Lorentz transformations, do some algebra, and actually figure out how this works. So when we do that, x2 is going to be gamma times x2 minus vt, and we're going to subtract that from gamma times x1 minus vt, because that's x1 prime. And so what we're doing here is we're just taking this and we're just substituting our variables in from the Lorentz transformation. What I hope you all notice is that vt in these two terms, they drop out because they actually cancel each other. And one of the hallmarks of that this is a length contraction and not time dilation at all is that time is measured the same when this is being moved. We're only talking about speed. Not speed. We're talking about length. So that's why these t's are the same, and then they will eventually cancel each other out, through the algebraic process. So what are we left with? We've got gamma times x2 minus x1. Oh wait, we just saw that over here. So we can say now like L prime is equal to gamma times L, but usually we don't want to talk about that. We don't want to talk about the non-inertial reference frame because usually we are in the inertial reference frame. So the answer to length contraction would be the length of the object that you measure is whatever its length is going to be at relativistic speeds divided by that function gamma. So that's how you find length contraction. In the next videos, we'll go on to relativistic mass as well as relativistic momentum and energy later on. So good luck in your studies, and may the force be with you.